Okay, so to study the order topology, we will need a simply ordered set. A simply ordered set is a set defined using an order relation. So does anyone know what is an order relation? No.
Oh, sorry, I forgot to switch on my microphone. So order relation is like when you have like specific rules, like you define order with A, B, and I think that it's not reflective and it's transitive and it's
Yeah,
totally not symmetric.
exactly. We have three properties for order relations. Uh, an order relation is a binary relation which satisfies the process of anti-symmetry, transitivity, and reflexivity. An order relation is transitive if for every three elements of a given set X, if X is in relation with Y and Y is in relation with Z, then X would be in relation with Z. For example, if we have X greater than Y and Y is greater than Z, then X would be greater than Z, right? Reflexivity. R is reflexive in a set X if and only if for every element of X, X is in a relation with itself. For example, X is always equal to itself, and X is always very smaller or equal than itself. And anti-symmetry relation is anti-symmetric if and only if for every two elements of a given set X, if A is in relation with B and B in relation with A, then A would be equal to B. For example, A is this, and we have B is smaller than A, then obviously that means that A is equal to B. Right. Any questions? I can't hear you.
No, I kind of feel like we went over that before.
Okay, so okay. So we say that if X is a simply ordered set, there is a standard topology for X, which we are studying today. Uh, let's suppose that X is having a simple order relation. Then we have two elements, such as one is smaller than the other. Then we will have four types of subsets in X, and they are called intervals determined by N and B. The first one, second one, third one, fourth one, as you can see here. The first one would be called a closed interval. No, that's an open interval. Right. That's an open interval. The last one is a closed interval, and the two here are half closed intervals. Okay, and when we say that this interval is open, it suggests that it is also an open set when we put a topology on X, and we will see that after. Okay. So the definition of the order topology suggests that if we have X a set with a simple order relation, and we assume that it has more than one element, of course, and we consider the collection of all sets of these types. The first type would be all open intervals A, B in X. The second one would be all of the form half open, A0 to B, where A0 is the smallest element of X, if there is any, of course. And the third one would be an interval of the form A, B0, half closed, where B0 is the greatest elements of X, if any. Then the collection B would be a basis on a topology on X, and we call it the order topology. So if X has no smallest element, there are no type nor sets of type 2, and if X has no largest element, then of course there is no set of type 2. All right, that's the definition. So to check and see if X has an order topology, we'll have to check that to see if every element of X lies in at least one element of B. Right. So we have to check that X is in one of these intervals that we just saw here. Right. And we will have, and if there is any smallest element, it has to lie in the second type of sets here. And if there is any greatest element, it will have to lie in the third type of intervals. And we will also have to check that the intersection of any two sets of these types is one set of these types, or would be empty. Right. So if we have these conditions, then we can call B the order topology on X. Any questions so far?
Can you just get to previous slide so I can glance through it once more, if you don't mind?
What?
Can you get to a previous slide so I can just like,
Okay.
yeah, I could even finish making the notes, if you don't mind. Thank
Tell me if I'm going fast.
Sure, thanks. Where's my smallest element? Okay, so we don't have to have the intervals of type 2 and 3 if X is unbounded, right?
No.
Okay, yeah, makes sense. Thank you.
Okay. So that's a reminder of the definition of basis for topology. I guess you already have done that. Yeah, right? Okay, let's move to an example here. So if we consider a set R times R in the dictionary order, and we choose to denote every element of this set X times Y, it's just an arbitrary representation, and we can't say that R times R has a largest or a smallest element. So the order topology on this set would be the collection of all open intervals of the form A times B and C times D. Or it can also be the collection of all open intervals of the type A times D or A times B, where B is smaller than D. So here in the figure here, you can see, let's say this is B, right? And that would be D. Here, that would be A. And here, that would be C. So if X, for example, an element alpha is in the set R times R, then alpha would be between B and D. It would be greater than D and smaller than B, right? And it would be greater than A and smaller than C. So it would be here and here at the same time, which means that if alpha is an element of R times R, it would be here, like here. Does that make sense?
Oh yeah, okay, sure.
So here in the second form of intervals, we take A would be equal to C, right? So we will have only here B and D, but A is equal to C. That means that we will only have that. Then the set would be simpler than the other one, and every element of R times R would be here. All right? And that is the basis for the other topology on R times R.
Like, I have a very naive question. Like, the point, like, for example, AC is not in the open interval, right? Sorry, A. They're not. Okay, thank you.
No, wait a second. Yeah, they're not there.
Okay, okay.
Yeah. Okay, can I move to the next part? If no one has a question, then okay. So let's go back to X, that is an ordered set.
Wait a moment. Sorry, Othmane. So could you provide us maybe more examples about this kind of ordered topology? Like the easiest, simply ordered set should be R, right? Instead of R cross R, the R is easier.
Yeah, okay. So
Then,
let's consider the set R here, right? So the standard topology on R would be defined as it is defined on the usual R that we study. So let's take, for example, two elements, A and like A and B. Yeah, right. And the order topology on R would be A, and every element of R would be between A and B. And here, on the R line, we would have A, right, B here, and here is the sets.
yes. Then could you give us maybe a description about what would be the open set, or what would be the set on the topology of R? What kind of set could be on the topology of R?
It can be a set of the first type, like this one, right? And if we consider that R has a greatest element, which is possible, then it would be one of the second type.
Well, R is just R, right? Or the real number. So let's just take R.
If we take just R, then it would be an interval of the first type, right?
That's only the basis, right? The question I have is, what would be the set in the topology of R? Can you give us some description about that?
I don't understand your question.
Well, you see, this order topology, you gave the definition by providing a basis, right?
Yeah.
But then we say that, okay, if you have a basis, we will automatically get a topology.
Yeah.
Generated by the basis, right?
Yeah.
Then can you imagine what kind of set are in the topology generated by this open interval basis?
Then I think the basis would be the union of all intervals in R, of all types. Okay, 1 second. Yeah, B would be equal to, let's say that R is equal to elements A, B, etc. It's an infinite set.
Well, let's say, just take it easy. Let's say R is just the real number, okay? R is just R.
Okay.
Okay. Then what would be the well, what would be the set in the topology of this well, standard topology or the order topology you have?
The order topology would be the union of all intervals in R.
This is the basis, right? The basis of this topology is all the open interval, right?
Yeah.
Then what would be the topology?
I can't hear you.
I'm sorry?
What did you just say?
I'm saying the basis of this topology of R, right, of all the real number is all the open interval, right? We know that what does this open interval looks like.
Yeah.
But my question is, then what would be the set in the topology of this standard topology in R, all the real number? So how can you take it as an example to say that, okay, we have this basis, right? And how does this basis of the open interval generate a topology? What does it look like?
Can I help, Othmane?
Yeah, sure. I need help.
So I think what you can do is just try to guess that topology would be any kind of interval, both closed, half closed, and open. Well, we have open because we basically have all kind of open sets of that order, right? And then basically what we can do is we can show that we can take specific unions of open set that create half closed and closed sets. Like say, well, let me.
Is that possible?
Well, yeah, because in topology, you are only allowed to take finite intersections, but you're also allowed to take infinite unions, right? So you can,
so then can you take the infinite union to make a closed set from open interval from a lot of open interval?
Yeah, so
if
you, for example, want to, I'm just trying to figure out how can I write on this thing to, oh yeah, okay, great. So if we want like say x, oof, so bad, xy, well let's
say 0, 1, okay, to make it easy.
And so basically what we can do is we can take intervals that look like x plus 1 divided by 2 in the power of k, y, right?
Yeah.
And we can just keep on making this k bigger and bigger and bigger and taking the union of all such intervals.
So let me ask you a question. You want to make this half closed interval, x comma y, right? Or let's take x equals to 0, y equals to 1, okay? You want to find this half closed interval, say 0, 1, can you see it?
Mm-hmm.
Yeah.
So what you construct is those kind of interval. Remember, you want to create this kind of, well, open interval, take the union of it. This kind of thing, you want to take the union of all the k, right? This is what you want.
Yep.
Are you saying that these two are equal?
Aren't they? Because
so
I think
you got 0 for the 0, 0, 1, right? 0 is on this set. Is 0 on the union?
No.
Yeah, okay. You can do like this set was, but you cannot do a set with closed bracket, right?
Yes. So basically, the topology you generated by this basis is actually contains all this open intervals and the union, finite union of this well, not finite union, maybe infinite many union of this open intervals. Okay, so this is one of the characteristic of this well, topology. And another topology is, you can imagine there is another description about the basis and at the basis and well, how you can get the basis from well, how you can get the topology from the basis. I think it's on the which page? I think it's on page 80. Yeah, I think it's Lemma 13.2, something like that, I think, which basically says that, okay, an open set or a set in your topology generated by a basis is this kind of set, such that any point in this set, for instance, let's say A is in your topology of this R, okay, then what does A looks like? You can see that, okay, A can be seen as a union of some interval, okay? But then in higher dimension, it will be very weird. But then now what you can describe A is for any X in A, okay? There exists something in your basis. So which means there exists some kind of open interval, say AB, which is a subset of A, okay? Such that X is in this AB, is in this open interval.
Yeah.
Okay, so this could be seen as, well, another kind of description of the topology of R. So which
Okay.
means if one point is in your open set, this set is, well, this topology, the set in the topology is so-called open set. An open set in R is just saying that, okay, for any point of this open set, some closed neighborhood, there must exist some neighborhood such that this whole neighborhood contain this point is inside of your open set. Okay? So this is a description of this how does this older topology, the open set on the older topology looks like. Okay. Similarly for not only R, for some other set.
Okay, I see.
Yeah, this is just something I want to mention. Sorry, Othmane.
Yeah, thank you. Okay, so we will move to these types of sets, right? So if we have an element A of X, there will be sets in X that are called arrays determined by I, and they are like that, right? As you can see. So the sets of the first type here are called open and open arrays, right? And set of the last two types here, no, these two are called open arrays, and the last two types are called closed arrays. Right. So when we say that the array is an open array, it means that it's also an open set in the order topology. So if we consider, for example, the first set, this one. Okay. If, for example, X has a largest element, for example, B0, then this first set would be equal to A B0, right? These two sets would be equal. Any question here?
No.
And this set is the basis element, right? It is the third type of sets that we've seen in the definition of the order topology. So, and if we take another example, if X has no largest element, then this set would be equal to the union of all sets of the kind here, of the kind A, X. And we will have X greater than A. So this set would be the union of all sets of that kind. AX for X greater than A. Right. And in those two cases, we will have the first set would be always an open set. Right. It would be because it would be contained by X, and it would be contained by the basis of X. Right. Any question here?
Sorry, a very quick exercise. So can you prove that this set A comma infinity, this open set is actually equals to the union, just as you write, is equals to the union of AX, where X is greater than A.
Okay. So let's say this open ray here. This is the open ray. This is A. And this is plus infinity. And here are all the elements of the open ray, right? Let's say X is here, X0. Oh, sorry. This is X1, X2, etc., 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 X. So this open ray would be the union of this set and this set and this set and this set. And X n for every n, like in n, would be greater than A, right? And that shows that that proves that this open ray X plus infinite would be equal to the union of all sets of this kind, A, X, n for X greater than, right?
Well, Othmane, so I think the idea you got the idea, but what you write is not really a mathematical proof. Okay, so here I suggest you to try to write it in the maybe in the way of a set. Okay, like maybe I will just write something here. So you want to show, for instance, you want to show X is greater than A. This A comma X is equal, the union of this kind of interval is equals to A comma infinity, right? This is what you want to show.
Yeah.
Then how can you show this equation is an equation? Well, you just need to show for any element on the right-hand side, it must be contained in the left-hand side and vice versa.
Yeah.
Right?
Okay. So
yes.
Let's prove first that this set is contained is the other, right? No, let's start with the other one, right? Okay.
Okay.
Okay. So this is an operator, right? So the topology it generates is contained in the other topology, right? The topology they generate is contained in the basis of X, right? By definition. But if we want to prove the other inclusion, we have every basis element for the topology order equals a finite intersection of open rays, right?
I'm sorry, I'm a little bit confused. So what are you proving at this moment?
We are proving that this open ray is equal to the intersection of all these open.
The union of, oh, okay, the union of all this. Yeah, okay.
Yeah. So to prove that, we have to prove that the first set is contained in the other and vice versa, right?
Yes.
So let's prove first, for example, that A plus infinite is contained in the union of all these sets.
Okay.
So we have A is an open interval, right? Open set. We mentioned that before. So the topology it generates is contained in the order topology.
Wait. This becomes somehow like cycle. Well, so how can you prove that this is an open set?
Okay. This is a subset of X, right?
Yes.
And an open set is a set that is included in X, and it is a part contained by the basis of the topology of X, right?
I think this is, well, this is the basis of the topology. This B, right? B is the basis of topology.
Yeah.
And this A comma infinity is not in this basis. Is it?
No.
Right. So you still need to show this.
Okay.
So you can, yeah. Well, you may overthink this kind of problems. So if you want to say some set is a subset of something, then you just need to say, okay, any element on this set must be an element of the other set.
Yeah.
Right.
Yeah. Okay.
And I think this is something you argue before.
Okay, so let's try again. So we want to prove this AX, right?
Yes.
So we suppose that an element X is
maybe let's use Y because you use X too many times. Also on the right hand side.
Okay. Y.
Okay. Yes.
Y is
okay.
here.
Yeah. Y
So
is here.
that means that Y is greater than A, right? And this set suggests that X is always greater than A. And it is a union of all sets in this form, right?
Yes.
So we want to prove that Y is an element of at least one of these unions, right?
Yes. Yes.
And we have here is A, for example. Let's draw a line. So that's X1, X2, right, etc. So we want to prove that Y, we have Y is greater than A, right? Which means that Y would be here or here or here, etc. Right?
So you trying to find something, right? Well,
Yeah.
What are you trying to find? You want to find Y is in the interval A comma X, right?
Yeah.
So here you're trying to find, which means you're trying to find such X such that A comma X contains Y, just like in your picture, right?
Exactly.
Yes, great.
So there must be a set in this form, AXN, that contains Y. And if there is a set like that contains Y, that means that Y is greater than A and smaller than X.
So why this kind of X exists? It seems that you just pick up any Y, right? You just pick up some Y. Well, I'm sorry. You just pick up some Y such that this Y is greater than A.
There is a
Then-
lemma. There is a lemma that suggests that for every Y in a set, it exists an alpha in that set that is greater than Y.
Well, unless there will be one situation such that there does not exist another alpha such that this alpha is greater than Y.
Oh.
What if
Okay.
Y is the biggest element, right?
Oh, so
Which is why you have to exclude this situation first.
yeah, I get you.
Yes. Mm-hmm.
So okay, so let's suppose that what we're arguing here, we're supposing that Y is not the biggest element of the set, right?
Mm-hmm.
So now we have to study the case where Y would be the greatest element here, right? If Y is the greatest element, then this set would be equal to A Y, right?
Well, at least there is a subset. Yes.
Yeah. We want to prove that this is this set is a subset of the union of all elements of the type this, right?
Mm-hmm.
So we will have to
I think you already get it, right? Because you got some, for any Y that is bigger than A, you got some bigger element X, right? Or some bigger element Z, so
yeah.
that AZ is bigger than AY, or AZ is, well, AY is a subset of AZ.
Yeah.
Right? So you get, okay, Y is actually in A comma infinity, and it's also in the set of union of all this AX.
Yeah.
Right? So which means A infinity, A comma infinity is a subset of the union. And then you say that, okay, then if we have some, if we have this union, then it should be also the subset of A comma infinity, right?
Yeah.
And of course, it's true because you see that you have some A comma Y, then there exists some X such that AX is a bigger interval, right? And
yeah.
but then we know that, okay, actually your Y is in this A comma infinity because Y is greater than A.
Yes.
Right. So which means so you got that, right? For any point or for any AY as an open interval is actually a subinterval of A or a subset of A comma infinity.
Yes.
Something like that. Yeah. Okay. Yeah. Okay, great.
Okay, thank you. Okay, we can also say that these open arrays, they are in fact subbases for the order topology on X. So there's a reminder of what a subbasis is. So we want to prove that. As we just did, we will want to prove that a set contains the other and vice versa, right? So we want to prove that this set contained by S as such as S is a subbasis of X and vice versa. So these open arrays, these open arrays are open in the order topology as we just proved, right?
Oh, sorry. Would you mind reminding the definition of subbasis? Because, yeah.
Okay. Okay.
So subbasis is kind of like a cover of X.
A subbasis is like a subset of the basis, right? And it is collection of sets as such as if we unit all these sets, we find X. Right?
Okay, I see.
Okay. So we want to prove that A plus infinity is equal to S, right? So we already have, this is an open array, which means it is an open set, as we just say. So the topology is contained in the order topology, right? Because it is an order set, an open set, which means that we already have this inclusion. Okay, so we will have to prove the other one, right? So let's say every basis for the order topology equals a finite intersection of open arrays, right? This is by definition, as we just said before, in the beginning of this, right? So the interval AB here is equal to the intersection of B and right. Does that make sense?
Wait, sorry. Are you saying that AB is a union? Oh, do you mean an intersection?
Okay.
Okay, yeah, now it makes sense.
Sorry. Yeah. Does that make sense now? Yeah.
Yeah, totally.
And if we have a greatest or a smallest element, we will have sets in this kind of these kinds, right? And zero. If they exist, they are open arrays. Why? Because we just showed that if X has a smallest element, for example, then this set here will be equal to this one. If it has a biggest element, then this set here will be equal to this one, right? So these are open arrays, and these are open arrays, and this is equal to union of open arrays. And that means that AB would contain S. subbasis of X, right?
Wait, sorry. So you're saying that AB is in the subbasis because its collection gives you what?
Okay, wait. So, S is a subbasis of X, right? So it is collection of sets whose union is equal to X. And the collection of intersection of sets in S form a basis B on X, right? So let's say,
Yep, sure.
so let's say this is X, right? And in this case, we have a largest element B, smallest element A, right? So S is a collection of sets whose union is equal to X. Then S would be like union of elements like this, of sets like these. They are all in here, such as their union would give us X, right?
Oh, I got you. So you're saying that these two half-closed intervals give you a union from A0 to B0, but the intersection also gives you an open interval, which is a basis.
Which
So
is
that's
here, right?
why they are in
Right.
the
So
subbasis.
we have these two cases. This is the case where we have no biggest or nor smallest element. And this case, if we have the biggest and smallest one. In those two cases, A and B would be contained by S, right?
Yeah, sure, gotcha. But I think Tikan just joined, or maybe he joined. Hey, Tikan, do you understand what's happening?
I can see who joins and got them screen sharing.
Well,
I have some like unexpected conditions. So
okay, Teodora, Holly, just like ask questions if you have any.
So there is no question. This was the last paragraph of my part. If there isn't any, I can stop sharing.
Oh wait,
Are
are
you-
there any exercises in your chapter? Oh wait, did anybody say?
No, there is no excuse. These are the only, I have only these proofs.
Are you going to talk about example 4 of the textbook?
Which example?
Example 4.
Okay, 1 second. I didn't see it, so I'm sorry. Wait.
Can someone share your screen? Because I don't know what exercise is that. And like, maybe we can do it together. Or example.
Okay, do you have the example for you're talking about now? Because I don't have the
I can I can share the picture of it.
Okay.
Oh, that would be great.
Like, can you see it? Example 4.
Yeah, I can see it.
Did it have any continuation? Because I only see tildes align A1, A2, blah, 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 B1, B2.
Oh, wait a minute. Here.
What is saying there about that it's not a discrete topology? I don't particularly see that part.
Sorry?
So what does it say about, I see there's a paragraph started with order topology on X is not the discrete topology, but I can read further. What does it say?
Oh, it says the order topology on X is not discrete topology. Most one-point sets are open, but there is an exception. The one-point set B1. An open set containing B1 must contain a basis element about B1 by definition. Any basis element containing B1 contains points of the A1 sequence.
So what, because anybody understand why is it not open?
Yeah, I'm very confused.
Well, as far as I understand, like I see why it should contain like some elements that start with a whatever, because like B1 is basically like you're ordering in dictionary order, so there is nothing before B1 except for elements from A, so we have to get them to your open interval, but I don't see why your point B1 is not open then.
Well, you can try to look at the picture finger 14.1 and try to imagine what does that mean in this example, right? So first, B1 is in some interval. It's in some interval, say A1, common B2, right?
Yep.
Then what you want to make is, well, you want to make B1 as an intersection of an interval of this guy, right? And another one, which maybe contain something smaller than B1, but just smaller than B1. Right?
Not quite clear.
So, or you can just see this, well, this formula here. you can just write X as A1, A2, dot, 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 and B1, B2, dot, 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 right?
Mm-hmm.
Then you want to write B1 as the intersection of two open intervals.
Wait, we want it to be an intersection of two open intervals because
Otherwise we cannot call it an open set.
okay. Oh
Wait,
yeah,
well,
it cannot be in union, but okay. So it
yeah,
has
the
to
single
be,
element set is an open set. This is what we want to show.
oh, and it has to be a finite intersection, right? And
Yeah, it has to be a finite intersection.
okay, that makes
This
sense.
is the point. If you
Okay.
want to solidate this B1, then you have to get an infinite intersection. If you only got finite intersection, then there must be some A, which becomes the biggest element of this among this A1, A2, AN.
Okay,
Okay,
then I have a
that
question.
contains in your.
Why
Yeah.
other points are open?
Well, other point can always be, you can see that this set, this X, is basically seen, it can be seen as two lines, right? Two infinite long lines, or two rings. If you try to see it as two rings, then, okay, any other point is just like the intersection of two kind of sets, just like Othmane mentioned, something like well, minus infinity to a point that is greater than this point, and minus infinity to a point that is less than this point, exactly less than this point.
Oh, it can be minus infinity to B1 plus 1 and
Exactly.
and it just
Well,
B1
for some other
plus
element, yeah, it can be minus infinity to this element plus 1 and minus infinity to this element minus 1. But B1, it has no previous element. This is only exceptional point.
Wait, so you're taking an intersection of, why are we taking minus infinity 2 times? So aren't you taking then, if you want to take B2, aren't you taking then from like, say, I don't know, from like B1 to
B2 plus
plus
1.
infinity and then minus infinity to B3 or something?
You could, but if this element is not B1, then we can say that this is an open set, because we can choose to open interval such that the intersection is exactly only this point, right? This is something clear, I think. Is it?
Okay.
Maybe I can open a whiteboard. Is that possible? It doesn't work at this moment. Can I use this one? Okay. Yeah. Let me share the screen with you. I think this one. Okay. So for instance, you may have some element, let's say some C. What is it? Okay. Let's say we have some element C, okay, in your set X. And we want to show that this single element set is in the topology of this X, right? That clear? Then what we can do is there exists some element such that this element is just less than C, right? There exists some D which is less than C, and there doesn't exist something E such that E is between D and C. Okay, so and similarly, there exists something like F, okay, which is greater than C, and there doesn't exist some G such that G is between between C and F. Okay. Then we know that, okay, this single point set is equals to from minus infinity or from the smallest element A1 to D. I'm sorry, it's not this one. Well, where is okay. This point C is equals to well, from say from minus from D to plus infinity, intersect with from I think from minus infinity to F, right? Or you can write it as D comma F. Yeah, I think this might be easier. It's actually equals to D comma F. Is that clear?
Yep, sure.
Mm-hmm. But if you choose C equals to D1, this argument will not work because the first step is not true, right? If C is equals to B1, then there does not exist a previous element, right? Which means all the interval that contains B1 must contain infinite many elements in the sequence AN, right? Any interval, open interval contains B1 must contains infinite many elements in the sequence AN, right? And from 1 to infinity. This means if you only take a finite intersection of this kind of interval, you will not get a single B1, right? Because a finite intersection will not eliminate infinite many elements. Finite intersection must contains a biggest element. Not the biggest element. I should say, it must contains the biggest element that not in that is in this that is not in this interval, but it's in some it can be seen as some AM. Okay, so this is why.
Yeah, but why A1 is open?
Well, A1 is open because A1 is equals to minus infinity, or well, it's actually equals to minus infinity to A2, right?
Oh, okay, I see.
But yeah, I think it's or is equals to the half closed interval A1 comma A2, because it has the smallest element.
Oh, okay.
Yeah, sorry, I think my equipment is not here, so use some time to explain it. Anyway.
So who's presenting next?
I'm presenting on part 15.
Yay!
Just give me a second. Okay, so my part is about the product topology on X cross Y. So we start with the definition of the product topology on the cross product of two sets. So if X and Y are topological spaces, their product topology on X cross Y is the topology having as basis the collection B of all sets U cross V, where U is an open subset of X and V is an open subset of Y. So now we have to prove that B is a basis, and so the conditions that a basis has to meet are firstly for each small x. First, I'm sorry I did not include this in the presentation. I just thought that maybe because we talked about basis and subbasis before in every section, it will be okay if I just read it out. If someone is a little bit confused, the page with the definition for basis is page 78 and subbasis is on page 82. So the first condition for basis is that for each element of the topological space, there is at least one basis element B which contains it. So since by definition the basis contains the entire topological space X cross Y, then it contains every element of it as well. And the second condition is that if X belongs to the intersection of two basis elements B1 and B2, then there is a basis element B3 which is a subset of the intersection of B1 and B2. So what we have here in the second point is basically a proof that if point small x small y belongs to the intersection of the cross product of U1 and V1 and the cross product of U2 and V2, then step by step we get that the point xy belongs to the cross product of the intersections of Uy and U2 and the intersection of Vy and V2, which by definition is the basis element. I'm sorry, I just see there's someone writing something. Okay. Okay. So yeah, we get that the point xy belongs to B3, which is a subset of the intersection of B1 and B2. I think like the little proof right here, it's not too hard. Maybe I can leave it for a while on the screen so you can go through it and read it. And then we can move on to theorem 15.1. Okay, so I will move on to theorem 15.1. If someone has a question, maybe we can talk about it now or later. I don't know. So, did someone say something?
Oh no, sorry, that was me lagging. I wanted to ask if that's only for me that the connection kind of interrupts time to time, or that's
Okay. I hope your connection is okay. My connection was pretty good up to that point. Like I could hear everyone clearly, and I did not have any interruptions. So okay, we go to theorem 15.1, and its statement is that if B is the basis for the topology of X and C is the basis for the topology of Y, then the collection D, which is the collection of all sets B cross C, such that B belongs to the basis of X and C belongs to the basis of Y, is a basis for the topology of X cross Y. So for this proof, we'll need Lemma 13.2, which says that if C is a collection of open sets of the topological space X, such that for each open set U in X and each element X of U, there is an element C belonging to this collection, such that X belongs to C, which is a subset of U, then the collection is a basis for the topology of X. I guess that when it's read out like this, maybe if you don't remember the last talk, it won't make a lot of sense. So it's on page 80. And so our proof goes like we have an open set of X cross Y, which we name W, and then we have a point in it, which we name little x cross little y. So by the definition of the product topology, there exists a basis element U cross V, such that X cross Y belongs to U cross V, and U cross V is a subset of W. So since B and C are bases of X and Y, it follows that we can choose an element B from big B such that X belongs to B, which is a subset of U, and an element C from C such that Y belongs to C, which is a subset of V, and little x cross little y belongs to B cross C, which is a subset of W, and by Lemma 13.2, T is the basis for X cross Y. And this is quite useful in our next example. So as Othmane talked a little while ago about the order topology on R, so the product topology of the order topology with itself is the standard topology. So by definition, its basis is the collection of all products of open sets of R. But if we apply theorem 15.1, we can define its basis as the collection of all open intervals on R, as we see down here. And this makes it a little bit smaller and easier to work with, I guess. So like something which I was confused at first with the example, why would it be like such a difference to have between the open set and the open interval in the basis, but basically we remember that the open set on R contains unions of open intervals in R. So when we deal only with open intervals, we don't deal with all the unions which are not open intervals by themselves. And so the next definition which we have is a definition for the projections of x and y to x and y respectively. I see there's someone writing something in the chat. Example 4 is the same as the product topology. I don't, let me see. So I do not consider this. I will have to take some time to think about it. So Professor Xu asked in the chat if example 4, which we just discussed, is the same as the product topology. Okay, so
Wait, what was the example for? Oh, when we did order of like 1, 2 was the product of like z?
yes.
Ooh, okay. Can you go and show what the product topology definition is again?
Yeah, sure. It's here.
So well, we know that Z is a topological space. Oh wait, we never proved Z is a topological space, right? Well, we'll just have to prove that set of 1 and 2, and then Z is a topological space, and we'll be done, I guess. But does anybody remember what definition of topological space is?
Let me go back. I think it had something to do with. Okay, so a topology. So a topological space is a set X for which a topology T has been specified, and then the prerequisites for topology are that first the empty set and X are in the topology, then the union of the elements of any subcollection of the topology is in the topology, and the intersection of the elements of any finite subcollection of the topology is in the topology itself. So, Professor Xu, will this go like if we can define a topology on Z plus, and we can define a topology on the set of 1 and 2, then can we say that set X, which is 1 and 2 cross Z plus, is the product topology?
That looks legit. Okay, then shall we just try to prove it to like find a topology on those sets?
Okay. So can we, I think we can, for the set of 1 and 2, we can define a discrete topology.
Yeah, we can just do, I think we could do empty set 1, 2, and 1 and 2, and it would be a topology because we have all the unions and all the intersections, and we have empty set and the whole set, so it should be a topology. And then for Z, I think if we just take set of all the subsets, it should be it.
Can we define like an order topology for Z? Okay, so both can be discrete. And then, so since we can define topologies on both 1 and 2 and Z plus, they're topological spaces, and then their cross product would give us a product topology. Okay. So can I move on to the definition of projections? Anyone? Okay, I will move on to the definition of projections. So if we have, if I define two functions which are pi1, which maps x cross y to x as pi1 of x, y equals x, and then pi2 maps x cross y to y such that pi2 of x, y equals y, then those two maps are the projections of x cross y onto its first and second factors. So, just let me find my notes. These two projections are surjective, since for every small x which we get, there exists a product xy which gives us this x, and unless x or y are empty, those maps are surjective. And if U is an open subset of X, then the inverse function of pi1 of U gives us gives us U cross Y, which is open on X cross Y. And if V is open on Y, then the inverse function of pi2 of V equals X cross V, which is again open on X cross Y. So this allows us to define a subbasis of the product topology using those two functions. So theorem 15.2 says that the collection S of when I tried to prepare my presentation, I tried to read it aloud and practice how it's going to sound, and I was really confused about how to read this one. So I'll try. So the collection S is the union of the collections of the inverse function of pi1 of U such that U is open in X, and the inverse of pi2 of V where V is open in Y, which is basically all sets of type. And this collection is a subbasis for the product topology X cross Y. So when we go back to what is a subbasis, we know that a subbasis for topology on X is a collection of subsets of X whose union equals S. So we also know that the topology defined by the subbasis is the collection T of all unions of finite intersections of elements of S. So the proof goes on like we first denote with T the product topology on X cross Y, and then we denote with T1 the topology generated by the subbasis, and then by the collection S. So every element of S belongs to T, since if you go back to the definition, it can be translated to some form of a set U cross V, which is an X cross Y. And from this follows that arbitrary unions of finite intersections of S belong to T as well. So thus we get that T1 is a subset of T. And then for every basis element U cross V equals the intersection between pi1, between the inverse function, the inverse of pi1 of U and inverse pi2 of V, which is also a finite intersection of elements of S. So T is also a subset of T1, and as the two topologies are equivalent, and S is a subbasis for both, or they're the same topology. And that's about it. Does anyone have questions or comments?
I'm kind of a little bit confused. So basically what we did is we took all kind of pre-images, but like set of pre-images for U and V, and we know that they're open, and we took their collection. And what you're trying to say is that if you, that all elements of S would be in the topology, but then I'm kind of like not, so you're creating a topology generated by S, and then you're showing that it's equal to the product topology on X cross Y.
So maybe if we go to this part that every element of S belongs to T. So basically going back to our definition, our basis for product topology is all sets U cross V, where U is an open subset, V is an open subset. So this our elements of the topology would be unions of such elements U cross V, and here.
Well, I was out, so I think you just you use this kind of push forward or push back to define your product topology, right? By this projection. This is a very, I should say, very standard way to define or to induce a topology. Okay, if at the very beginning you have some kind of chronic map or some nature map, and you want to have some kind of chronic topology or the nature topology based on this map, then this would be the, you will see that this would be the best way to define those kind of topology. The reason is, well, I think several sections later, you will see that the motivation or the major motivation for us to study the topology or to study this topology course is just because we want to make a better understanding of map or the continuity of a map. When you discuss about the topology, it will always be connected to the continuity of a function, okay? And if you want to discuss the continuity of a function, as I think you mentioned, the continuity of a function is not defined by this image stuff. It's defined by the pre-image, which you will see that later. So which means if you try to use this kind of push back or push forward, backward kind of definition, then you will get this kind of projection to be a continuous map, okay, in some sense, which we will see that later. So if you want to make this kind of thing nature or chronic, this kind of map is continuous chronically or naturally, then you will have to define your topology in this way or somehow, well, weaker way, okay? You may want to define your topology to be no stronger than this kind of definition so that your projection would be a continuous map. This is something you will see that later, okay? At this moment, you just see, okay, it's just some kind of pushback. And maybe you can see what kind of pushback or what kind of this kind of pool map looks like, or how does it looks like in, say, R2. If Teodora, you can do that, you can just share with us what kind of open set induced by this kind of definition is an open set in R2, okay, based on this kind of thing. And you can see that it's just those kind of things which more or less like something like AB cross something like A to infinity or B to infinity or C to infinity, this kind of set, okay? This is just a comment.
So the topology which is generated by this subbasis would be the collection of all unions of finite intersections of its elements. So I'm going to write this down and think a little bit more about it.
Yeah, if you don't understand it at this moment, it's totally fine. Okay, because it just well, this kind of definition is kind of, or this kind of theorems, you don't really see the motivation at this moment. It's just some trick. But then in the future, you will see that it's kind of important because it can somehow say that you have to have this kind of thing. Otherwise, the projection map, like you do the projection of from R2 to R, this projection map, if you don't have this kind of topology, it may not be continuous. If you try to visualize what it looks like, it's just like a strip, okay, an infinite strip on R2. Well, you try to visualize it on R2, then this kind of well, pushback. For instance, if you try to push back A common B, which is an open interval in R to R2, what does it look like? It would be A common B cross R, right? Which is an infinite strip, either vertically or horizontally, right? Because you have these two parts. So if you want to treat it as a subbasis, if you want to get a basis, then it would be the intersection of this kind of infinite strip so that you get this rectangle. And this rectangle, all these kind of rectangles can form a basis for the topology, the natural topology on R2, just as what you're trying to imagine.
I just opened the page which contains this theorem, and there is a very good figure which explains what you just said. Thank you for the explanation. I was staring at the figure wondering why is it the way it is. Now it makes sense. So our topology will be like unions of all of these rectangles. We have to imagine it. A binding union, the union of, yeah, rectangle. Okay, so are there other questions or comments? Maybe we can take a 10-minute break and continue with the next part. No.
Yes, no problem for me.
Okay. I think we'll take a 10-minute break and continue then with part 17, I think 16, sorry.
So shall we resume now?
Yeah, okay. Is everybody here? So can we start now? And okay. The chapter 16. And we need to first define what is the subspace topology. First, let X be a topology space, and Y is a subset of X. And then the topology on Y can be defined as Y intersects with the open set of X, U, which U is an open set of X. So the topology of Y consists the topology of I consists of all the intersections of open sets of X with Y. And now we need to prove that this topology of Y is a real topology. First, the first condition is easy. The empty set is in the topology of Y, and so is Y itself. And the second condition is finite intersection of the open set in Y is also in Y. So this is the open set in Y, and intersects with finite open sets. This one is equal to the intersection of all the UN, of all the U, and then it intersects with Y. And then the third condition, the third condition is arbitrary union. For example, in the index sets alpha. It's also the arbitrary union of the open sets of Y is also in Y. So you can write it in this way. Intersects with Y. Do you have any question? Then now we're going to discuss the first lemma. It's about the relation of the basis and the subspace topology. Lemma. If B is the basis. It's the basis for the topology of X. Then the collection BY, defined as B intersects with Y, such that this B is an element of the collection B. Then this is the basis of the subspace topology of Y on Y. And to prove this, do you guys have any idea how to prove this? Oh, then okay, I'll prove it myself. First, we can find a given a open set U in X. Open. And then any element Y. Any element Y in the open set of Y. We can choose a B. Choose a B such that any Y belongs to B and contain in U. We have this Y is in the intersection of B and Y, which is also contains in the intersection of U and Y. Do you have any question about this proof? Then okay, I'll go on. The other lemma 2, we need to it says if U is open in Y and Y is open in X, then U is open in X. Now prove this. It's very simple. Prove here. We can find, and since U is open in Y, then you can write in this way: Y intersects with the V for some V open in X, for V open in X, open in X. And since Y and V are both open in X, and then so is Y intersects with V. Now we can see that U is also open in X. Okay.
Well, don't you need like a? Oh, okay, yeah, sure. I see what you're doing. Okay, yeah.
Okay. Have any other question? Okay, then we'll discuss the relation between the product topology and the subspace topology. Okay, so A is a subspace of X, and then B is of Y. Then A times B is the same as A times B as the subspace topology. Oh, sorry. As a subspace of X times Y. Like, do you have any idea how to prove this? It's Simple, very simple.
Oh, wait, can you repeat? So A is a subspace of X and
B is a subspace of Y.
okay.
And the first A times B is the product topology on A times B. And the second one is the topology inherits as a subspace topology. We need to prove they are the same. Do you have any idea how to prove it? Okay, then I'll prove it myself.
Oh,
Okay,
wait,
so-
can you give us one more minute and also remind us a definition of a subspace?
Oh, yes, of course. A subspace is the, for example, the subspace y of x is written like this. Ty is the y intersects with u when u is an open set of x. Open.
Wait, so what's here is a subspace? I don't get it. So like, you mean the second one is a subspace?
Yes, this yes. The product topology on A times B is the same as the topology A times B inherits as a subspace of X times Y.
Okay, so maybe we can try together, Teodora, Taka. So what I was thinking about is that basically we know that since A is a subspace of X, it's just basically the same topology with X, but just intersection with some U. And then B is like just has like the same topology as Y, but just an intersection with some open set V. And so I think before in the beginning, we did that thing and we showed that like a product topology of two like subsets, well, like yeah, it's just would be like a cross product of X intersection U and Y intersection V. So that's one thing. And from
Yeah.
the,
Yeah, keep going. You're very close.
and then from the other side, we'll just have to show what the product topology on AB is. Well, I kind of forgot the definition. What was that? Product topology on. Oh yeah, wait, but that should be like, because basically we show that the topology that A and B inherits from X and Y should be some topology of X intersection with U, cross product topology of Y intersection with V, and this is just like topology of A, product topology of B, and this is
Yeah.
what the product topology is. Okay, yeah, sure, that should be it.
Yes, yes. So it's U is the open sets of X intersects with A, and then cross B intersects with B. And V is the open set of Y. And this is equals to U cross V intersects with A cross B. And this U cross V is the element of the subspace topology of X times Y, X cross Y. And then A cross B, so this whole thing is the subspace topology of A cross B. So we prove this lemma or theorem. I can draw a picture here. So here, this is C and D, and this is A and B. This whole thing is the intersection, and we can see the this A intersects with C is times B intersects with D is just the same as this DC and BD intersects with each other. Okay. So now we are going to discuss the substrate topology, the relationship or relation of substrate topology and the order topology. I'll first give you some example. Example one. The subset Y is equal to 0 and 1 of the real line R. So it's the subspace topology of R. And the substrate topology has a basis has as basis all sets of the form the interval AB intersects with Y, where AB is is obviously an open interval in R. So the topology of Y itself is the same as the topology of Y that inherits as a substrate topology on R, which is just very apparent because it's this subspace topology of Y can be written like this. It has 4 forms. First one is like this. If A and B are both in Y. The second one is like this. If A is not in Y, and similarly this one, and if it's empty or Y itself. Okay. So in this form, the order topology on Y is the same as its subspace topology inherits from R. But there are some there are some other topology that doesn't follow these rules. For example, if Y is the subset, half closed set 0 to 1, with 2, then this order topology is not this order topology itself is not the subspace topology on Y inherits of the real line R. Because this one point set 2 is not open. It's not open in the order topology on Y, because we cannot find an open interval that contains 2 but does not contain any other basis element. But if it's a subspace topology, we can always find, for example, if it's 1 to 2 in R intersects with Y, then this 2 is open. So now we see these two topology are not the same. What if we want these two parts to be equal, we need to add one more condition, which is which I will first introduce the concept of convex. So, do you have any question? Okay, then. So if Y is a subset of Y of X is convex. Of X is convex. Then if for each pair of points A and B of Y, the entire interval AB of points X is lies in Y. Oh, sorry, lies in Y. Okay, so the intervals and rays in X are all convex in X. Now I'll introduce the last theorem. Let X be an order set in the order topology, and Y be a subset of X that is convex in X. Then the order topology on Y is the same topology Y inherits as a subspace of X. Order is the subspace. Okay. Do you have any idea how to prove it? Or I can give you some minutes, you can work on it. Do you have any thoughts?
Sorry, it was lagging for me for a couple of minutes. So from what I see on the board, you said that ordering X by having like subsets of X is the same as having like subspaces?
Yes. The X is an order topology, and Y is a subset of X that is also convex in X. And this order topology on Y is the same as the subspace topology Y inherits from X?
Oh, so we basically have to prove that. So we basically have to find a topology on X and find an intersection of that topology with some open interval next so that it becomes like a topology for Y, right?
Yes. Yes.
Okay, yeah, sure. And what's the definition of convex again? I'm sorry, it's really hard to remember so many definitions per day.
Oh, no problem. Like I just read it. If y is convex in X, if for each pair of points A smaller than B, like for example A smaller than B of Y,
Mm-hmm.
the entire interval A B of interval of X is lies in X.
Oh, so
Lies
for
in-
any points A, B in Y, the interval A, B lies in X. Okay, sure.
Yes.
Makes sense.
Just a quick comments on it. So convex here, it just says that, what's the convex meaning? Or what's the meaning of convex or a convex shape in some other, like in R2 in the plan? That just means that if you have some shape, you want to say it's convex, then that means on this shape, if you choose arbitrary 2 points, then the line connecting these 2 points are also inside of this shape. Okay, this is the meaning of convex. You can imagine, for instance, we may have some kind of circle, right, or disk. Then 2 points of it, you take the intersection, then this whole line are inside of this disk. But however, if you have this kind of shape, like a heart, then if you take 2 points of it, you want to connect them, then with some part of this connection, some part of this line is not on this shape. So this is not a convex shape.
Oh, so to prove that, maybe we should show that basis of Y, basis of topology of Y, when intersected with specific open interval gives us basis of X. Guys, any ideas? Like I don't know the solution myself, so I'm just guessing.
Yeah, this very close to what textbook is saying. Actually, I'm not very, I don't understand this very well. So it's basically they're using the subspaces, and prove it in two direction. First is, and then it's this one. So I'll just prove it myself. I'll show you the proof. Okay, so the sets the ray A to infinity intersects with Y, and the minus infinity to A intersects with Y. It forms a subbasis for the subspace topology on Y, right? Like this part is a subspace subbasis of X and then intersects with Y. So this whole parts are also open in the order topology. So now we can say that the subspace topology is contained in the order topology space. Oh, sorry, too bad. Order is subspace, whatever. And the same logic can be used reversely. At the open rays of Y, for example, B to the infinity of y in y equals the intersection of an open ray of x with y, since y is convex in x, right? So it is open in the subspace topology. It's also open in the subspace topology on y. And since the open rays of y are subbases for the topology on y, so the order topology is also contained in the subspace topology. Now we can prove that they are the same. Okay. Do you have any question? Do you have any question, or I'll keep on? Okay, then maybe we can do the exercises together.
Well, I think I'm fine. Teodora, Tekan, Othmane.
We still have half an hour.
Yeah, hey guys, can you give some kind of a sound that you're here? Okay, Teodora gave us thumbs up. Hey Teodora, did you get like entire lecture? Because we have half an hour. We can always get to some parts that were not clear. Oh yeah, we noticed you weren't here. We suppose it was some kind of a technical issue. Maybe you want us to get to a part when you were absent and we can talk more about it.
I can introduce the example 3. I still have one example that I haven't talked about.
Sure.
Yeah, it's a little more complicated. So it's the product topology I in it's interval 0 to 1, and then the dictionary order on I cross I, which is the restriction on the plane R times R, okay, R cross R. And this order topology, this dictionary order topology is not the same. It's not the same as the subspace topology. It's not the same as subspace topology obtained from the dictionary order topology on R times R. Order. Like, do you have any idea how to prove it? Or give an example why it's not the same, why it isn't the same. Dictionary order. Subspace.
So the question is to show that the dictionary ordered I cross I is not equal to subspace I cross I?
Yes, the subset I cross I under the order dictionary order of R cross R, like R2. They're not the same.
Wait, and how do we order I cross I?
Okay, I'll show you this. The picture on the textbook writes this. For example, the here. The sets 2, 1, 2, 1, cross, 2, 1, 2, 1, closed. It's an open set of the subspace topology, but not the order topology. I guess because this thing here is closed. The one here is closed.
I kind of have to go to the textbook back. Give me a second.
Okay.
Okay, so can you explain why this set wouldn't be an open in one case and be an open in another case?
Oh, it's just my guess because I'm not very sure about this. And in the subspace topology, we can have, for example, 2, 1, for example, 2, 1, 2, 0, and then cross with 2, 1, 2, 1 in 2, 1, 2, for example, 2 in the order topology of R square, and then we intersect this with the I cross I. We can get this 2, 1 cross 2, 1, 2, 1. Oh, sorry. Here should be 2, 1 as well. This one is open in the subspace topology, but it's not open in the order topology, which I don't quite understand why it isn't open. So my guess is that the point 2, 1 half and 1 here, this one is not in the interval. It's not an open interval.
Yeah, I'm trying to understand why, because it's kind of like important, but So what was our definition of open in topologies? It was like if it's like in the topology, like an element, right? Why is it an element? So you say that it's an element of subspace topology. But not in order to follow. That's so weird. Guys, any ideas?
I think you can just check it, for instance, by visualization. What is first? It is open in the subspace topology. Why is that? Why it is open on the subspace topology?
Because it can written as the intersection with an open set of x of r square and with y, with
Yes.
the
So it can be seen as one piece of this vertical line, right? The intersection of this one piece vertical line and this rectangle or this square. But then we need to know what is the order topology on this square.
Wait, can you go back to 6? So you're saying that it's the intersection of a line with a square, but when you take a square, shouldn't the square be supposed to be like open too? In a sense.
Well, that's a very good point. Is that necessary to have this? This set itself, this subspace, must be an open subspace. We introduced this kind of example before, which is example 1 in your textbook. In example 1, we try to check the subspace topology of 0,1 closed interval, right?
Yes.
So which means if we study the subspace topology, it's not necessary to have this subspace to be open itself, open on the whole space. It's not necessary. Which is why we could study this order square, right? Although it looks like a closed set, but it doesn't matter. Any subset, we can study the topology on it, inherent from the whole set. Okay, so it doesn't matter whether it's open or not. Yeah, of course. Then the next thing we need to double check is what is the topology, what is the order topology of this square, right? The order topology is again just like the picture, the figure 16.1, right? It's what? It's just you try to collect all this kind of line, and then you try to. It's like the Forden of all this kind of line. Okay, like a zigzag of this kind of line, right? Can be seen as this something like a zigzag of this kind of line. maybe not zigzag. Think it's something like this kind of thing, right? And here, this point will connect to this point will connect to this point, and this point will connect to this point. This is a dictionary order, right? And then, and then what would be the open set on this kind of this kind of Forden lines? Well, it must be, we try to stretch it and make it a whole line, and then try to draw the open interval on it, right? Which is why you can see that this set, just as Holly said, is not an open set, just because you have this one here, right? Because if you try to draw this set on this kind of Forden line, on this kind of line, well, it will look like what? It will look like this part, right? It will look like this would be a half, and it would be looks like this part, right? So this part from the graph, you can see that it's not an open interval. If you try to unfold it, then it will not be an open interval, right? So which is why this set on this older topology is not an open set.
So are we like connecting all these lines into one long line, and like this one, and we have this closed interval here, so it's closed?
It's not closed, it's just a half open, half closed, right? So it's not open.
Okay.
Yes. So this is an idea about the older set, this dictionary older topology. It's a little bit weird, but it's just something you try to treat this kind of two-dimensional stuff like one-dimensional stuff. This is
okay.
idea.
Okay. Okay. I see. Thank you. So are we going to talk about the exercises, or we can end this day now?
It's up to you guys.
So what do you think? We still have 10 minutes left. Then, okay, I'll just talk about exercise 1, which is relatively easy. Okay, so we have a subspace Y of X, and then A is a subset of Y. Open, let's see here. Sorry, subspace. And then the topology A inherits as a subspace of Y is the same as the topology inherits as a subspace of X. The Ty is equal to Tx. Like, do you have any idea how to prove this? The topology A. A inherits as a subspace of Y is the topology inherits as a subspace of X.
Can we solve this by applying the definition for subspace topology twice? Or we have the we get the topology of let me see the name. So we get the topology of X. Wait, is a subset. So we get firstly the topology of Y generated by S its subspace of X, and then we get the topology of A, like the subspace topology of A, and then we show that it's a subset of the topology generated by the subspace topology of Y.
Yeah, basically the same. Oh, okay, you're basically right. So we can the topology on inherits as Y is can be written like this: A intersects with V, and this V is open Y. And the topology generates as X inherits from X is A intersects with U, right? And so this one can be written as A intersects with the U intersects with Y, right? Because Y is the subspace of X. And then since A and U are all subsets, sorry, we can, is also equal to A intersects with U and then intersects with Y. Right? Since A is in Y, so this whole thing is inside Y. So we can remove this Y, and this two equation this two is